Hi everyone. Hello everyone. Can you hear me? Please let me know if you can hear me. Hi everyone. Okay, so now let's get started. I think I'm audible, right? Great. So we will see in this session, we will see paging. Okay, and we will understand paging in very depth. So basically you can attend this session even if you have not seen any lecture of operating system, or even if you don't know anything about operating system. Okay, still you can attend this lecture. Most probably you will be able to get everything, because paging is you can say one of the separate topic from other topics like scheduling, deadlock, okay, synchronization. So paging is one of the very separate topic, so you can directly attend this lecture. There is no issue in that. Okay, great. So by the way, today I have uploaded one video, since only 3 months are left, and we have uploaded one video. Have you seen that video? Okay, most probably, right? Most probably you have seen this video. Okay, so nice to hear that. Now let's just start our lecture, which is paging. Okay, so let's get started. So you can see my screen, right? Just let me know. Okay. So basically, this topic is, you can say, one of the less understood topic to many of the aspirant, and also this is bit of the frequent topic, which means gate generally asks from this topic, okay, in every year or every 1 2 years. So let's just get started. Okay, so about the session, people are saying yes, sir. It was very motivating session, a motivating video that today I have uploaded. So there was one video with the title called "A Reminder Why Go Classes." Okay, a reminder why go classes. So something like this, I have uploaded one video. Okay, over the YouTube. If you want, you can just search on the YouTube "A Reminder Why Go Classes." Okay. So I've uploaded just now, and I was just asking if you watched that video. Great. So many of the comments are here. They are saying, "Yes, sir, I have watched. It was really motivating. Thank you so much." So now let's just start our topic, paging. So by the way, paging is not a really new idea, which means that we have been using paging since a long time. Okay, and in fact, if you are reading a book, okay, let's see. Generally, like currently in the gate preparation, we don't have time to read either the novel books, or like some fiction books or something, but because we are very much involved in the lecture, so and also we tend to not read much of the standard books. So but you know this, right? So every book has some index, index table, and this is the page number. So every book has the page number. So this is the same kind of idea, that we will be maintaining one index. That index will be having that, okay, this topic is at this page number, something like this, right? So there are two things. One is that this is the page number, and another one is this topic. Okay. So let's start with a very basic idea. Let's suppose you want to write a C program. Okay. And whenever you're writing a C program, let's suppose there is some C program that you're writing. Then the moment you hit the run button, okay, the moment you run this, see, you might be knowing that there is something called compile. Okay, if you don't know directly, then that's fine. So basically, there is something called compile, and then after compilation, you are going to run it, right? So it's something like this. So I'm talking about the run. Okay, the moment you run this, then what will happen to this particular C program? The moment you run this, you will be seeing that it must be loaded into the main memory, and this basically, this get converted to something called as process. Okay, see, the terminology is like this. This is called program, or you can call it code. Okay, program, and this is called process. So once you run this, it is a process because now it is running, right? Now, suppose there is a process. This get converted into some process which looks like this. So basically a process is a separate entity than this program. So what will happen once you run this? It will be converted to something called as process, as you can see on the screen also. See here that this is the process, and process means that there will be a virtual memory of this process. So the virtual memory is some topic that you will get to understand over the this lecture. So basically there is a memory which is very logical memory, you can say. Okay. Virtual memory and logical memory, both names are actually same. So you can also say logical memory. The moment it get converted to the process basically looks like a logical memory, which means like process has its own logical memory, which is, let's suppose, 0 to 2 power 32. Okay, suppose this is the process logical memory, which means that whenever you run this program, this logically we are going to say that okay, there is some memory which is allocated directly to this, okay, only to this. And this is just a logical memory, there is no physical existence to this memory. And then a little bit you might be knowing that okay, we will be storing code, and then there will be heap area, there will be stack area. So it will be something like this, like heap and stack grow opposite to each other, right? So the thing is that this is the logical memory, and we have to basically keep this sanity alive, which means that we want to make the programmer or make this code feel that okay, there is a logical memory which is like this. But ultimately, it has to go into the physical memory, right? I mean, ultimately, it has to be stored. Maybe see, suppose I ask you something, that this is what you want. Okay, this is some logical memory that you have promised to the compiler. Okay, or compiler has promised to the code, so whatever, right? So basically you can say it is logical memory. Okay, this is some logical memory. Now now according to let's not make things complicated, let's just keep it simple. So suppose according to us, okay, according to us, this is how the program look like. I mean, once you load it to the main memory, it should be getting its own logical memory. Now ultimately it has to be stored into the physical memory, right? Now the thing is that suppose this is just I'm asking you, okay, suppose this is, let's suppose, 2 power 20 bytes. Okay, suppose this is 2 power 20 bytes or 2 MB or 4, let me just say in GB. Okay, let's suppose this is 4 GB. Let's suppose this is 2 GB. Can you store directly? Tell me, can you store directly? Can you store directly? If this is 2 GB, this is 4 GB. Suppose I'm just saying to you, right? And tell me, can you store directly here? The answer is yes, right? Why not? Obviously yes, right? So the answer is yes. So basically, I can definitely say that we can store it directly. Okay, I hope this is very very easy and very clear. That okay, suppose I'm promising to my program that you will be getting basically 2 GB memory like this, where stack and heap will be growing like this. Okay, this is my logical memory. And suppose in the physical memory I have privilege to store directly, then maybe I can actually, if someone asks me can I store, then yes. But it is not always the case, right? It is not always the case, which means it might so happen that this is more. Let's suppose this is 8 GB. Okay, suppose this is 8 GB. This is more. In that case, can you store directly? Tell me. In that case, can you store directly? So can we store directly? The answer is no, right? I mean, obviously this is 8 GB, this is 4 GB, so how can I store this, right? So, see, the thing here is that these two things should be independent. I mean, I'm not restricting myself. okay, or to promise to the compiler, or compiler is not restricting to promise to the programmer that the logical memory should be lesser than physical memory or something. Okay, basically I want this logical memory to be independent of the physical memory. Okay, I don't want the restriction that okay, if it is can I store directly or not, or something like this. Currently no, right? So basically these two concepts should be independent of each other. That's what my desire is. Okay, should be independent of each other. That's what I want. So the question remains like this: the in reality, basically, the logical memory and physical memory can be of different sizes, or and the sizes could be greater, lesser, or anything, right? But the question remains here is that then how to store? Okay, how to store? This is the question that we want to answer, and the answer is paging. Okay, so how to store? This is the question. The answer is paging. Basically I will say, actually the whole key point here is that this is kind of, you can say, invalid or something, right? I mean, there is, I mean, whenever a stack will grow, then only it will grow, right? This is huge space, this is huge space. Generally this is extremely huge. Generally, let me just tell you that what is, a typical, in a typical system, there is a setting. Let me quickly go to that slide. Actually, that was not relevant here, but okay, let me just reveal the suspense. See, let's just do a reality check. Okay. So what is a reality check? It means that whenever you write any program, doesn't matter. Okay, doesn't matter. Whenever you write any program, this is almost in the bytes. Okay, I mean, there will be, static area will be stack, and heap will not grow more than bytes. Okay, maybe 100 bytes, 500 bytes. I mean, they will not generally be reaching in the kbh. Okay, not even be reaching in the kbh. In the sense that, in reality, whatever program you have, okay, any general program, whatever you have, they will not be basically going to the going more than kb. I mean, it is basically, in this case, let's suppose it's 35 bytes only, but generally it is not more than kb. Basically this is total. Okay, if this is, let's suppose, 4 GB I'm promising, okay, 4 GB I'm promising, then out of this promise only generally we are using 1 kb. Okay, not more than 1 kb. I mean, this is extremely huge space, almost 99% of the space. Okay, you can say it is 99.9% of the space. This is huge space which remains empty. And the paging says that if you want to, okay, if you want to store, let's suppose, this is a huge area which is empty. Okay, if you want to store this, then don't store it directly. Okay, don't store it directly. Even though if you can store, let's suppose, don't store it directly. Say that I will just part this into chunks. Okay, I will just divide this into chunks, and I will store only the filled area. Obviously this remaining area, why I am going to store, right? This remaining area, there is no point in storing. So basically, I mean, because there is a garbage, I mean, there is nothing here. Okay, so basically what I'm saying, paging is saying that, see, this huge area is empty. So that is why, let's do one thing. Let's just divide this virtual memory, okay, into some pieces. Okay, some chunks. Let's just divide this virtual memory into some chunks, and then store these. Okay, I mean, till this point, all of these and all of these. Okay, don't store in between. Okay, no storage, something like this. Okay, so basically, to make it happen, what we will do, we will basically divide first virtual memory into some parts. We are calling those parts as pages. Okay, so the term here is very fancy, and it is called pages. Okay, this is called pages. So basically, we are calling them pages. How many pages are there? Okay, nice term, right? So we are calling just them pages. And then what we will do, we will divide this physical memory also into parts. This is actually very interesting, to be honest. Okay, see, the statement is actually not very true. What I'm going to say now, that see, I just told you that we are going to divide this physical memory into parts. Actually, this is not entirely true. See, logical memory division makes some sense, but physical memory is a huge, like, it's like a universe of memory, right? I mean, this is the only reality. This is the existence of memory that you have, right? Just because you want to store something. Okay, can you divide it? Just imagine. See, there are many things will be there in this particular memory. Maybe operating system code will be there. Someone is storing, let's suppose, some files, right? Some movies. Okay, I mean there are many things could be there. I mean not movies basically. I mean generally the running process is only there. But yes, so OS code and anything. I mean there are many things because someone is storing integer or someone is storing something, right? So you can store anything here. Just because I am want to store one of this, okay, one of this, then the size of this is basically looks like this, so I should be dividing this also into the same size. It is actually not entirely true. Like we don't divide the physical memory. It is conceptually true that we divide the physical memory. Okay, I will just tell this in the detail in the future slides. But basically conceptually I'm saying that we are dividing the physical memory. Okay, and we also divide this into the same size. Okay, that we want to fit in. Basically we want to fit these pages, so we will divide this also into the same size. Let's suppose this is 1 MB page. Okay, then here also 1 MB pieces. So each piece here is, let's suppose, 1 MB, then each piece here is also 1 MB. Now this piece can go anywhere, this piece can go anywhere, this piece can fit in any frame. We call them frames. Okay, so here the name is page, here the name is page. Size is actually same, but the names are different. Okay, we call it frame. Okay, so final frame, you just imagine a frame, right? You have a wall frame like that. I mean on the wall we have some photo frame, right? So kind of that. I mean ultimately in that frame we fit something, right? So you are going to fit this page into the frame. Is this fine to everyone? Okay. So basically now just for my sake of understanding, I'm saying that I'm dividing this in the frame, and this is actually true. I mean, even if you take it very by hearted, like for example, the physical memory is divided into the frames. Okay, without any other knowledge, if you take it very by hearted, then I think it is even better. Okay, because if you don't get confused, so just take it like that. Physical memory is divided into the frames. Okay, and then we are going to fit this page into the frames. Now, how all of this process is going to happen, right? So by the way, all of this process is called paging. So the whole process of storing these pages, dividing into the pages, or all of this, okay, it's called paging. So before I proceed further, is the idea clear to everyone that what we are going to do? Okay, so we are going to fit this into the frames. So let me just summarize this in this slide, and then I will just revise whatever we have just covered. So pages, we will divide this into the pages. We will divide this into the frames. They could be any. Let's suppose this is 4 GB. This is just 2 GB. There could be, I mean, any number of pages, any number of frames. Okay, they need not to be same. Sizes need not to be same. Okay, of physical memory and logical memory. So now any page can go to any frame like that. Okay, very independently they can roam around. I mean, it's not necessary that okay all of these pages should be contiguous. There is no need actually. Why? Because we will be maintaining all of this into something called as page table. So basically we will be having a page table here. We will say that okay, this is page 0, page 1, page 2, page 3, like this, page X. Okay, so page 0 is actually has not gone to any. I mean, let's suppose it has gone to. Okay, let me tell you about page 1. Page 1 has gone to frame Y. Okay, so I will write Y here. Sorry, Y at Y here. Okay, page 1 is going to frame 1. Page 2 I'm not showing here. Page 3 is going to frame 2. So page 3 is going to frame 2, like this. Okay, I will maintain something like this. This is called page table. And now I have the index. Okay, I know that okay, page 0 is going where, page 1 is going where, page 2 is going where, page 3 is going where. Okay, so is this fine to everyone? Now, now let me just summarize that what we are doing. Okay, so basically we are saying that we have basically borrowed this idea from this book kind of concept, where we have the page numbers and we have the index table, right? So from that, well, I mean, there we call it index table. Here we are calling it a page table. That's the only difference. But we have kind of borrowed the idea from here. Okay, so suppose you have a C program, then once you start running this, then there will be a virtual memory for this. Okay, we are or logical memory. So we are promising it. Okay, that there will be a logical memory, based on that the program will run. Now, how to ultimately fit this logical memory into the physical memory? Because ultimately there should be the physical existence to the things, right? So how to fit? That is the all I can say burden that we have currently. So directly fitting is not a good idea because there is lot of huge waste. Okay, I mean there is not this area is not filled. So directly fitting, even though we can fit, it is never a good idea. So the thing is that we will divide, okay, into some chunks, some pieces. We are calling it pages, and we are also going to divide this physical memory. Okay, we are also going to divide this physical memory into the same size. We are calling them frame. Okay, so the size of page and size of frame is same, and now any page can go and fit into any frame like this, and then we will be maintaining all of this idea into the page table. Okay, so is this understood? Okay, great. Now, so basically we also call it logical address space or physical address space. I mean, what is the space? So let me just tell you the meaning of the word space. So logical address space or physical address space. I mean, what is this address space means? So let's suppose you have logical memory of 2 power 32 bytes, suppose, right? So see, it doesn't matter whenever we are thinking logically. So basically, it doesn't matter whether it is logical memory, physical memory. Ultimately, we will treat it as a memory. So basically, in this memory, the whole space of this memory, okay, this is called logical address space. I mean, the space of memory. So basically, address space means space, the whole space, the full and empty both, including both. Okay, the whole space of memory. Space of what? Space of memory is called address space basically. Okay, so if it is logical memory space, the whole thing, it is called logical address space. Similarly, if it is physical memory thing, then we will call it, I mean, if this is physical memory, we will call this whole space as physical address space. Okay, now someone is asking, for every process will it have a virtual address space, separate virtual address space? Yes. So actually this idea I have discussed in another video, but for now let me just tell you, yeah, to answer this question, yes, for every process there is separate logical memory. That's the promise. Okay, I mean, that is the whole system, that is how the whole system is working. That while you are writing the program, at that time you don't need to worry about the physical memory and all. You can just say that, okay, for you independently there is a separate logical memory. Now how this logical memory is ultimately fitting into the physical memory, this is the abstraction. Okay, this is not of the interest of the programmer. You're getting my point? So basically the idea is very simple for the programmer, or someone who is writing the compiler, okay, or the programmer, you can say in general. So the idea is very simple. Okay, they do not want to confuse the programmer. For a programmer, they want to make it happy whenever you are writing the code. Okay, suppose you are basically writing a code. Suppose this is your laptop. I don't know if the drawing is okay, but yeah, suppose this is your laptop, you are writing a code. Okay, at that time you just think one thing. Okay, just one thing you can think, that there is a logical memory. Okay, of, let's suppose 2 power 32 bytes. Okay, suppose. Okay, then how ultimately, see, now your job is done. Okay, then you can write the program thinking that there is a logical memory of 2 power 30 bytes, 32 bytes. Now very nicely this idea get converted to the physical memory, and that's the job of operating system, and that's what we are learning, because the subject is operating system, right? So we are learning this is the operating system, how the operating system is translating this logical memory kind of concept to physical memory. Okay, and that's very nice concept, and the whole idea on which it is based is basically that there is a huge space between a stack and heap. Otherwise, obviously, if there is no space, then how can you can fit multiple programs into the physical memory? Okay, so I will come to that point, but is the idea clear that we want to make this programmer happy? Okay, so that it need not to worry about that, okay, how much there is a space left in the physical memory, or how many programs might be running simultaneously if I run this program. Just all tension free, just assume that in terms of the memory you have the logical memory, and that's all. Okay, don't worry about anything else. Now operating systems are providing that abstraction, you can say. Operating system, is providing that abstraction. It is converting this logical memory to the physical memory. Is this okay to everyone? So does every process has the its own logical memory? Then answer is yes. Okay, yes. So every process has its own separate logical memory. Okay. So I hope this is clear to everyone. This is an interesting point. Is this understood to you? So whoever asked this doubt, is this understood to you? So Ravi, Sailendra, is this understood? Okay. So how does the page table look like? It will look like, see, suppose this is how you are mapping. Okay. Then ultimately, how does the page table look like? It will look something like this. It will look something like this. Which means we will say, we will say that this page one is mapping to, let's suppose, okay, some frame, I'm calling it six or any frame. Then basically we will just have the accounting, okay, that page zero is mapping to which, page one is mapping to which, like that, right? We will have that accounting. And accounting is very important here. Okay. So this accounting, we are calling it page table. So basically just an array. Okay. Actually, this is just index. You don't need to store it. Okay. This is just an array. Okay. You can store these in an array. Page table is an array. So page table, you can say, is an array where index I will tell you that where does this frame, this page I is getting stored to. Understood? So basically, we are dividing this logical address space. We are dividing this physical address space. We are storing this logical address space pages into the frames, and the accounting is done by the page table. Okay. So now let's just do this question that what they are saying. A system uses a paging with a page size of 4 KB if the logical address space contains 2 power 32 bytes. How many pages are there? So they are saying that logical address space size is 2 power 32 bytes. Page size is 4 into 2 power 10 bytes. K means 2 power 10. Okay. K means 2 power 10, which is 2 power 12 bytes. Now, if this is the page size, okay, so basically this is a whole logical address space and the page size is something like this. So how many such pages will be there? You can just check 2 power 32 divide by 2 power 12. So which is 2 power 20. 2 power 20 such pages will be there. Okay. Pages will be there. Is this okay to everyone? So the question was easy. Answer is D. Okay. So here you can say the answer is D. Let's see this question. A process has a logical address space of 8 pages, but only 5 frames in physical memory. So basically, they are saying in the physical memory, there are only 5 frames. Okay. So these are the 8 pages. 8 pages you have, suppose, is logical address space. In physical address space, suppose you have 5 frames empty or total 5 frames, doesn't matter. But yeah, these are 5 frames. Now, how many pages at maximum can be in the memory at the same time? 5 only, right? At maximum, there could be only 5. Okay. Because there are no more than 5 frames which are available. Okay. So at maximum, there could be 5 frames could be present in the physical address space. So basically, what about the remaining pages? Remaining pages generally, if this is not currently in execution, okay, we store them to the hard disk. Remaining pages we store them to the hard disk. Understood? So the remaining pages get stored to the hard disk, and whenever we want to execute them, then there is something called page fault. We bring that page to the physical address space, and then we do the job. Okay. So if it is not in current execution, we store it to the hard disk. Understood? Which of the following statements about logical and physical memory is true? Logical memory is always smaller. Logical memory is always larger. Always smaller. No. Logical memory can be larger than physical memory. Yes, can be, is true. Both are equal? No, it is not necessary. Yes, both, like they can be, right? They can be larger. Yes, this is true. If the logical address space is 1024 bytes and each page is 16 bytes, how many pages are in their total? So I think we have done this kind of question. 2 power 1024 means 2 power 10 divided by page size is 2 power 4, 2 power 6 pages, right? So this is logical address space size. Okay, this is logical address space size. This is the page size. Then you are getting number of pages, which are 2 power 6, which means C. Understood? Okay. So basically, basically here 64 pages, right? So you can see those 64 pages like this. There will be page 0 to page 64. And since each page is of how many bytes? 16 bytes, right? 16 bytes. So each page is of 16 bytes. So you can say that byte number 0 will be here, byte number 1, byte number 2, and byte number 15. Okay, till byte number from 0 to 15, there will be something like this. Okay, I mean byte number 0 is arranged here to like this. Okay, and then this is basically 16, 17 like this, right? Okay. By the way, looking at this, can you tell me, byte number 17 will be in which page? Byte number 17 is in which page? Byte number 17 is in which page? Tell me. See, it is very clear that byte number 17 is in page 1, right? It is in page 1. So the answer is, you can say answer is page 1. It was very simple question. I hope you understood this. So basically, I'm just asking that if you're dividing into 16 bytes, then 0 to 15 will be will be in the page 0, then so on and so forth, right? Okay. So byte number 17 belongs to which page? See how we can do this. That we can see something like this. See, we are dividing into pages, right? The whole address space we are dividing into pages. This is second page. Let's suppose this is the third page. Okay, this is the fourth page. This is suppose third page. Suppose this is fourth page, and so on. Okay, so basically what I'm saying, that if each page is of 16 bytes, right, then if I want to ask 7 byte number 17, then I can just divide 17 by 16, because if each page 16 16, it will be in the multiple of 16, then it is 1 point something. So just I can just keep the integer part. Okay, keeping the integer part, then I will get to know that this byte number or this particular address is in which page. Okay, you can just divide with the page size. This is the page size. Is this understood to everyone? Okay, so basically suppose this is 17, and then we can just divide this 17 with the 16, then whatever is the page size, I will be getting 1. Suppose I want to know where byte number 0. Okay, suppose I want to know byte number 0. Byte number 0 is in which page? 0, right? Byte number 1 is in which page? It is also 0 point something, so it is basically integer part is 0, right? Similarly, if I want to ask you, let's suppose byte number 16 is in which page? 16 divided by 16, it is 1, so it is in page number 1, isn't it? Is byte number 16, isn't it, in the page number 1? So basically if I have the page size, then I can just divide, okay, the address, whatever the address, this is the byte number means the address, right? I can divide the address and I can get the page number. So the integer part will be the page number. So let's solve more questions. Suppose I want to ask you byte number 130 belongs to which page? See see every has every has 16 bytes. Okay, 16 bytes. I just want to know that what is the multiple, I mean the integer multiple of 16, which gives you nearest to 130. So basically 130 divided by 16. Can you do this? So 130 divided by 16 will be 8.125, which means 8. This is the integer part I can take. Okay, so basically what I'm saying, that if you have like if you have 8 I mean this is the you can say the page number. So which means which means that if you have this 130 as your logical address, then this logical address will be in the eighth page. I mean the page number 8. Okay. Why that is the case? Because these will be, see, the page number is starting from 0. Then let's suppose this is the page number 8, right? This is the page number 8. Since it is starting from 0, okay, then you can see that above this, okay, above this page, can you tell me how many pages are there? Tell me. So above this page, how many pages are there? Yes, 8 pages will be there, right? Eight pages will be there. So you can say there will be the 8 pages above this page. So basically, I mean, roughly you can say 16 into 8, which is till 16 into 8 is 128, right? 16 into 8, 128. So basically, you can say till 128 byte, these are the things. And now from the next bytes, like this particular page is starting, and then 130 will be somewhere here. So how to get, this is very important, how to get, the page number. For example, let me just make it very easy. Suppose that page size is 5 bytes. Okay. I'm just keeping you very simple, 5 bytes. Okay. Suppose if I ask you logical address space, logical address. See, this is just for our calculation. Generally, it is in 2 power. Okay. So just for the sake of understanding, I'm writing. Suppose if I ask you, where is this 32? Okay. Logical address 32 is in which page? Is in which page? Then what will you say? You will say that 32 divided by 5. Then I'm getting 6, right? So basically, it is in page number 6. Why that is the case? Because this 32 will be after at least 6 pages. Okay. After 6 pages, there will be till 30 only, right? And then 32 will be there. Okay. So this 32 will be after 6 pages. So how you can get it? 32 divided by 5, which is 6. Okay. So after 6 pages, it will be there. And this after 6 pages, actually, there will be the page number 6 because the indexing is starting from 0. Okay. So after 6 pages, it will be there. And this is also the page number. Why? Because the indexing start from 0. But anyway, let's not make it complicated. I hope you understood. Okay. For byte number 130, what is the offset? Now see here, if you understand, let me just go back here. This is basically 6.4, right? Yeah, 6.4. So what does this mean? It means that 6 is page number and 4 is basically generally called as offset. Okay, this is called as offset. So let me explain you very clearly. Let's suppose that you have, okay, I already have one diagram. Let me just copy that diagram. Suppose that you have these pages. Okay, suppose, I hope this is visual. Now page number 1 also has sorry, byte number 1 also have page 0, byte number 2 also page 0, like this, right? But how much is the offset for this and how much is the offset? Offset means how much down you need to go. So basically, this is the offset, right? I mean, basically you need to go 2 down. For example, here, okay, this is the boundary. It is 16 and then 17. Okay, so basically, just to get 16, you don't have to go anything down. I mean, 16 is directly. For the 17, the offset is 1. How much down you have to go? This is called offset. Okay, how much down you have to go? So basically, how to calculate the offset? See, the page number you can calculate by dividing. Okay, for example, this is 18. Okay, let me do the same calculation for 18. 18 has offset as 2. Okay, because you have to go 2 down. 16 and 17, you have to cross 16 and 17, then you will be getting 18. So 18 will be having the offset 2. So how to get the offset? The page number you get like this, right? So it will be uh, 16 divided by 18. It will be 1 will be the page number. and there will the reminder. Okay, so there will be the reminder I generally write like this: 16. The reminder is basically 2, and this reminder is called offset. This is called offset. Okay, offset means how much down you have to go, and you can calculate this by the reminder. For example, if I want to know what is the offset for 130, okay, then 130 mod 16, you can just calculate it. It will be 2. Okay, why? Because 130 is nothing but uh, 8 into 16 plus 2. Okay, so basically the remainder is 2. 2 is offset, which means 130 is in the page number 8. Okay, so this 8 is telling you that, I mean, 130, if you divide by 16, it will be 8. Okay, the integer part. So this 8 is telling you that this page, okay, this page number is 8, where the 130 lies. Okay, this page number is 8, and in this page also there are many bytes. You have to go 2 down. Okay, you have to go 2 down. 1 and 2 you have to skip, and then you will be getting 130, byte 130. Okay, is this okay to everyone? So basically the offset is clear to everyone, right? So how we are going to get the page number? Page number is basically just like dividing by the page size. Okay, just a second. Or the frame number basically. uh See, so the page number and offset, there are like two things which we have just discussed. So the page number you can get by the integer division, and the offset you can get by the modulation. Okay, so I hope this is clear to everyone, that how to get the page number and offset. See see suppose it was 32. Okay, 32 byte number. I think, let me give you the very simple example. Suppose the page size is 5 bytes, right? Suppose the page size is 5 bytes, and suppose the logical address is 32. Okay, byte number 32. So 32 divided by 5, you will be getting 6. Okay, this is called page number. And 32 mod 5, you will be getting 2. This is called offset. I think earlier I got 6.4. 4 is not offset actually. We need to take the mod. Okay, this is called offset. So what does this mean? That this 32 will be in the page number 6. Okay, it will be in the page number 6. And in this page also there are many bytes. Then you have to skip 2 bytes, and then you will getting this 32. Okay, so what does this page number 6 means? That page 0, page 1, page 2, page 3, page 4, and page 5, these pages will be, okay, above it, and then there will be the page number 6. Okay, and each page is of, let's suppose, 5 bytes. So you can say how many pages are above this. See, this is the page number 6, but how many pages are above this? 6 pages, right? 6 pages. So basically you can say 6 into 5, 30 bytes already you have covered. Then 2 more bytes you have to cover. Okay, then this byte is basically your 32. 2 more bytes you have to cover. I hope you are getting the point, right? Actually, you will get to understand even more with the examples. suppose suppose they are saying that, let me go to the next page, the logical address space is of 2 power 10 bytes. Okay, and page size is 8 bytes. Okay, which is basically 2 power 3 bytes. Now can you tell me what will the number of pages here? It will be 2 power 10 divided by 2 power 3, which is 2 power 7 number of pages. Okay, 2 power 7 will be your number of pages. Is this fine to everyone? Great. Now suppose they say that there is logical address which is 905. Okay, and they want to ask you the page number corresponding to 905. Okay, so what is the page number? Can you tell me? Corresponding to 905. So what we have learned, basically this is 905, right? Now there are two things. One is the page number and another one is the offset. So what we have understood is that if you want to find out the page number, then 905 divide by what is the page size? Page size is 8 bytes, right? 2 power 3, 8 bytes. Okay. And then here 905 mod 8. Okay. So let me know what are these answers. So if you divide, then what you are getting? So basically you will be getting here. Let me write here. You will be getting 113 point something. Okay. And here you will be getting just one. Okay. The remainder is one. So what I'm saying here is that you will get to know that page number is 113 by the division, and you will get to know the offset is 1 by the modulus operation. So you will be getting both. So which means that if this is page number 113, then how many pages are above it? There are 113 pages above it, right? So 113 into 8, these many bytes above it. Okay. And then after that, how much you have to skip? So basically, if you do this, this is 904. Okay. Then you have to skip one byte. Okay. You have to skip basically one byte, and then you will be getting 905. Okay. Because the indexing start from 0 actually. Okay. So I hope you are getting my point. So basically, if you want to find out the page number and offset, then you can do like this. Actually, there has been very recent question in GATE based on just this concept. Okay. In GATE 2024, they asked similar question. Understood? Now suppose you know that corresponding this 113 is getting stored at the frame number 10. Suppose that we know that 113 is getting stored at the frame number 10, which means the edge it is 113, the whole 113. Okay. 113. This is page number 113. This will get stored into the physical memory ultimately. And we are saying this, let's suppose this is frame number 10. If this is frame number 10, then how many frames are above it? 10 frames, because the indexing is from 0. So basically 10 frames above it, right? And then we know the desired byte. So basically offset was 1, right? Offset was 1. Then we know the desired byte is after 1. Okay, after 1 you will be getting the desired byte. This is the desired byte. I mean, here this is the desired byte, right? Now, since you're shifting this edge, it is, then here also the offset is 1. I mean, offset never get changed. Whenever you shift the page, the frame number obviously will be somewhere. I mean, it is not exactly equal to 113. It could be anything, right? The frame number will change, but the offset, because within this page you are not making any change. You're just shifting edge it is. So offset will be just 1 only. Okay. So can you tell me what's going to be the physical address space, or the physical address corresponding to this 905? Okay, which is logical address 905. What is the corresponding physical address? You can say it is after frame number, after 10 frames, and each frame size is, let's suppose, uh, 8 bytes. Okay, after 10 frames you are there, so this is frame size, and this is after 10 frames you are there, and then also I have to skip one more. Okay, so 81 is the physical address. This is the physical address. Understood? Okay. Based on this concept, actually, Gate has asked a very recent question. Okay. So how we are doing it? We are basically saying that if you want to know, uh, given the logical address, if you want to know the page number, then you can, let's suppose this is anything, okay, 905. Then it is 905 by 8, which is 113. And then we get the offset, which is 905 mod 8, which is 1. Now, if I want to know the physical address, okay, physical address, then I can say like this. So from here, that this 113 will get converted to some frame number based on the page table. Okay. Let's suppose it is stored in the frame number uh, 10. Okay. 113 is in the frame number 10. Then offset will not change. Okay. Offset as it is, which is 1. And this is done by the page table. We need the page table to translate the page number into the frame number. And then ultimately from here, okay, this 10 into the frame size, because there are 10 frames above it, into the frame size plus 1, which is basically 81, right? Ultimately you get your physical address. Okay, so basically let me just do a small detour, okay, and then we will just come back to this. So suppose I want to divide some numbers by 10, and similarly I want to divide some numbers by 2. Let's just see that how does the division happen. Suppose if I divide by 10, then if I just ask you the reminder, then you will say that this last two digits divided by 100 divided by 1000 means last three digits will be the reminders. Okay. And suppose what if I divide by 2? Suppose some number I'm saying, what if I divide by 2? Can I say the last digit or something? No, right? I actually need to divide. Okay. But in binary, division by 2 is actually very easy. Okay, very easy. How? If I do the divide by 2, then I can say that last bit is my answer. I mean, is the remainder. If I divide by 4, I mean 2 power 2, then last two bits are my answer. Okay, which is 10. 10 means 2. Okay. If I divide by 2 power 3, then last three digits are my remainder. Okay, which is 110, which is 6. Are you getting my point? You can try this. You can do in decimal also. You can do 16 to 2 mod 8. You will be getting 6 only. Okay, you can just check. Okay, so basically what I'm trying to say here is that if you want to divide some numbers into in tens power, then last digits in decimal system is answer. But if you divide in two powers, okay, then you can write in binary and last bits are your answer again. Okay. So suppose there is a logical address this and which I can write in binary, and there's a page size is this. Can you tell me the page number? How does it be, how do we tell? We basically divide this by 4 KB or 4096 bytes, right? Then we tell in the decimal. But if you have this binary, then can you tell in direct? Can you tell directly? Yes, you can say last 12 bits your answer. Okay, this is your page number. Sorry, this is your offset. And how many times do we divide is basically given by the remaining after the offset, whatever is remaining is basically given by that how many times we are going to divide, basically the page number. Okay, so what I'm trying to say here is that last k bits, if you have page size of 2 power k, then you can say last k bits are page offset and the remaining bits are page number, n minus k, which are remaining bits are page number. Okay, so this is very important slide, which means suppose someone give you, okay, let me basically do some exercise. Mm, Okay, I think, yeah. So maybe let me just do some gate question and then you will get to understand. Suppose, okay, I think this is one exercise. Let me first do this. Okay. So suppose there's a 8-bit virtual address and 10-bit physical address and page size is 64 KB. So basically, let me write the virtual address space, which is 8-bit. Okay. And if the page size is 2 power 6, then you can say these many will be used for offset, which is the 6 bits. And remaining 2 will be your page number. Okay. And similarly, for the physical address space also, okay, for the physical address space also, you can say whatever it is, this is 10 bits. Now, since the page size and the frame size is the same, so 6 bits are for the offset, frame offset or the page offset. Okay, remaining will be the frame number. Actually, in binary, it is very very easy. Okay, in binary, you can just say that okay, the bits, okay, the last 6 bits are offset, and this is the page number like that, right? Now here they are asking how many virtual pages will be there. So basically, this is the if the page number is basically given by the 2 bits, then you can say 2 power 2. Okay, 2 power 2 virtual pages, which are 4 pages. How many physical pages? 2 power 4, which is 16. 16 physical pages. How many entries in the page table? So they are asking how many entries in the page table. It will depend on number of pages. So number of pages are the 2 power 2, which is 4, right? Now, given this page table, what is the physical address for 241? Okay. So, what is the physical address for 241? We need to divide 241 by 64 to get the page number. And then, so if you do this, can you tell me what is the answer? So, 241 divided by, okay. So, you will be getting 3, right? So, it was easy division. And now, if you want to get, the offset, then how you will be doing? So, you will be basically saying 241 mod 64. This will be the offset. And using this, right? So basically, if the page number is 3, then this is the page number 0, page number 1, page number 2, page number 3. So page number 3 is getting stored at frame number 8. Okay. So using the page table, we get the frame number. So basically, page number 3 is getting stored at the frame number 8. And then you can solve this question. Okay. So now let me know, are you people getting? Okay. So, do you want to do one thing? Like, actually, I wanted to cover the complete paging in one lecture, but I think this is like too optimistic to do it. Okay. So let's just do one thing. I will be basically covering only the single level page table here. I mean single level paging here, and the multi level paging we will be doing it later on. Okay, in the next lecture. So this was a recent question which they have asked in GATE. Now what they are saying, the page table is given to you. Okay. Then they are saying that this virtual address which is given in the decimal, can you translate into the physical address? Okay. How to do it? Basically to translate, we first need to know the page number and the page offset. So what we can do, we can either represent this in the binary. Suppose we are representing. So by the way, sorry, this question was not in the GATE, but the similar question was in the GATE. Okay, this question was in our test series, in the mock test. We have asked this question in the test series, but the similar question was in the GATE. So suppose you are writing in the binary. Okay, suppose this is the binary format of your logical address. Now you can see this is the virtual address, which is 32-bit. Okay. Now you can see that you can divide this into two parts, 9-bit and 23 bits. How? Basically, these 9 bits are page offset, and this is because the page size must be 2 power 9. If you notice that page size is 512 bytes. Okay, because the page size is okay. So what about this? This is basically your page number. Now you can see this is the page number, which is actually this in decimal, and in the decimal, if you map this, so you will be getting the page number 300, right? So now 300 is this. So this is your frame number. Okay, the frame number is basically 300, and the offset will be as it is, and this whole thing is 13153,613. So that's how you can do it, but this is too complicated. I mean, you are converting the decimal to binary and then again binary to decimal. Instead of this, you can directly do with the decimal. Okay, so it is directly with the decimal. Okay, so basically how do you do it? You just divide it, and then you say that it is dividing these many times, which means this is the page number. So 5912589 divided by 512, this is 11548, this is your page number. And if you do the mod 512, you will be getting 13, this is your offset. Now, using the page table, you will get that, okay, this is corresponding to 300, right? So you can say 300 into the frame size plus offset. This is your physical address. 300 into the frame size is 512 plus offset is 13. Okay, this is your physical address. Now, this question they have asked in GATE 2024. Okay, so we have, by the way, asked this question way before than GATE 2024. I mean, we have asked this question in we had I also commented it that we had included this question way back in 2023, and to my surprise, almost every student who attempted the test at that time found it puzzling. It was surprised too that because it was simple question, and later I realized that students were not very familiar while solving problems using the decimal notation. And later on, Gate also asked using the decimal notation. Okay, so later on, 1 year later, Gate also asked using the decimal notation. Now they are asking that this is 2500. Okay, in the decimal, then what will be uh, the physical address? Okay, corresponding to this. That's what they are asking. Okay, so you can do in the binary or you can do in the decimal. Let me do in the decimal because that's very easy, because everything is in the decimal which is given here. So page number offset you can find like this, then you can find the physical address like this. If you do in the binary, then page number offset you can divide like this. Okay, then page number 1 is actually mapping to 11. Page number 1, sorry, 11 means, sorry, 3 here in the binary. Okay, so page number 1 is mapping to frame number 3, so which is 1 1, and offset is as it is, and then again you will be getting the same physical address. Okay, so you can do either in binary or in decimal. Okay, so now there are little more questions. Okay, which are basically gate questions only. And after that, like, we will be basically going to the multi-level paging. So actually, today I'm having little hard to speak. Okay, my throat is actually very blocked, and I'm having cold. So, can I? Is this okay? Can I just continue this is tomorrow? Is this fine to you guys? Okay, I'm really sorry. So today I scheduled this class, but I was having little cold. Not little, actually, it was too much. So I'm like finding it little difficult to speak. Okay, so I will just continue paging tomorrow. Okay, sorry about it. So thank you everyone. So actually I was having the jacket, so I thought that it will work, but it is actually not working. So thank you everyone. Okay. Take care.